All right, hi everybody. This is Stats 2.1 notes, and we're going to try to do these a little bit quicker today. Let's see how we do. Okay, so the first thing is you've heard before when you've taken a standardized test that you've scored in the top 90th percentile or something like that. Statistically, we have an official definition of that, and that is that the value of the pth percent, so that's like the 90th in my example, of the observations below where you are standing would be the 90th percentile. So if I said that there were 4 people standing here, and they were ranked in order so that the top person is over here, we'll give them a crown, okay? If we wanted to know what percentile this person is, we'd count below them. We'd say that's 2 people out of the 4. This person right here is in the 50th percentile, is at the 50th percentile. It's always the people below, okay? All right, so 100th percentile. Well, there's no way that I could count everybody below this person and still get 100% of them, so this is not really possible. That's why you'll often see percentiles will only go as far as 99. Is because we're always going below a person, and you can't have 100% if you don't count the person that's standing right there at the start, okay? So here's an example of that, of the people standing in a row. We're gonna look at them. I'm gonna pretend they're in order even though they're not. These are 8 students, so all of our fractions are gonna be out of 8. And the first one says, what percentile is a student that makes 6 baskets in a row? So here is the person that we care about. We're gonna count up how many people are beneath them or made less. So that's 1, 2, 3, 4, 5. So that is 5 out of 8. That is the 63rd percentile. Okay, and then if they only made 2, this is the person I care about. The person underneath that 2 would be only 1. So this would be 1 out of 8, and that would be the 13th percentile. Okay, so it's always below that person, right? All right, next one, I pre-filled in with us, so this would be a good place to pause if you want to. These are cumulative relative frequency graphs. Now we've already done relative frequency graphs and we've already done histograms. This is just another version that is accumulated percentages. So we've done these as histograms right here. We've done these as histograms, and we really could even do these now as histograms, and this is the new one. So this is out of all 51 states if you count DC. Of median household incomes. All right, so in the first one, we only had one state whose median income was less than 35,000. We figure out what that percent is. The next group up, they're the second group. There's 10 of them, right? So they're 20%, but the cumulative frequency is 11 of them, and 11 out of 51 is 22%. So you can see that we're combining them until we get all the way down to all 51, and we end up with 100%. Over here, they're still individual. Over here, they have been accumulated. Okay, so how does that affect our histograms? Well, they really don't change that much. Again, I've already pre-numbered these. Pause if you want to try to copy these each. Notice that there's this little Z in the front. That's just my way of saying I didn't start it at 0. There's a gap that I ripped off the paper, okay? And we are going to be looking at making these into little histograms. So the first one, these are counts. Right, they're how many states, the numbers of states. So the first graph, there was only 2 of them. And then the next graph, there was more. And then the next graph, there was more than that. And then the next graph, more. You get the idea. Okay, so there's my histogram of the different age groups. So remember, this one is going to be the 35 all the way up to 40, but not including 40, right? Okay, and then the same group here, this is going to be our relative frequency. So these are all going to be individual percents for each one of the states, for each number of the states. So the first one is like 2%. The next one is up here, and we're just converting them all into percents now. Okay, so we get the idea for that. All right, so notice that for counts and frequency, they are relatively similar in shape and nature, right? They have basically the same shape because we're just going from counts to percents. They should be in about the same shape, okay? When I go to cumulative frequency, already you can notice the pre-dots that I put there, that this is an increasing graph. As I move to the right, not one single dot went back downhill because we're accumulating. We're not accumulating any negatives, so it should keep increasing the whole time. Okay, so if I was doing a histogram for this, the first one would start out very small. The next one gets a little bit bigger. The next one gets a little bit bigger, and so on, because I'm continually adding in more to my accumulated percents until I reach 100. So anytime you're looking at an accumulated, so accumulated or cumulative percent, right? They can be as bar graphs, but they could also just be dots at those individual places, and you could just connect them as a line graph too. And they would just look like this. Okay, so after that, we should reach 100 at the top of every single one because we've accumulated them all. Okay, pretty easy stuff. These are called cumulative relative frequency. Relative frequency because they're still percents, cumulative because we're accumulating. This is also an old-fashioned word. They're called ogives. I have not seen the AP College Board use that terminology in a long time. They call them cumulative frequency, relative frequency graphs now. But ogive was the old-fashioned name for those. So if you ever hear anything like that, that's what they're talking about. All right, so what's the biggest difference between relative frequency and cumulative relative frequency? What's the biggest difference there? Well, relative frequencies are individual percents. Cumulative frequencies are accumulated or running totals of percentages, okay? Notice that if I asked you to do SOX to the first two graphs, it's not that difficult to do, but to do it to the cumulative relative frequency graph, there's a couple things I can pull out of this one, even though it's a cumulative. For example, if I wanted to know where the middle is, where the median is, right, that would be the 50th percentile. And I could say that the average annual income of all the states is around 45,000, right, something like that. So I can use that percentile to go ahead and find some of that information. So I can find 50th. I can also find 25th percent and come across and see where that hits and bring it down. And I could also do 75th and bring that across. So I can get my 5-number summary out of this by just using the percentages as my quartile numbers, right? Okay, so I can get to those. So I can get to my 5-number summary or something close to it, right? Is there anything else that I could get from it? Well, if I look at it as a regular one, I don't want to read this and say it's skewed left. They're all going to be skewed left. They're all increasing graphs, right? So if I'm trying to do any skew or any other shapes, I'm going to have to start thinking about it back like this if they really want me to do SOX to something about the data, about the actual average income. This is going to be very challenging to look at and try to say whether I think that it's skewed or not skewed. Also difficult to see outliers. So I'm going to say difficult to see shape or outliers, right? I could get spread from IQR or from range, highest minus lowest, so I could still do those from there, okay? How are histograms and ogives or cumulative relative frequencies different from each other? Well, in a histogram, it is usually counts for individual categories. And those categories are quantitative categories. In an ogive, it is a running total of percentages of quantitative categories. Okay. All right, and what percentile for the income of 45,000? So if I want percentile, that's the cumulative one. So I would want to know what is the percentile for 45,000. So I'm going to go back up to the table. I'm going to go look and see where 45,000 was included, right? And I want to know everybody that's less than 45. So since 45 is the dividing line here, I'm going to say that it is the 22nd, right? I want all of the incomes up to 45, but not including 45. So I'm going to say that that's a 22nd percentile. And then it says estimate the income for the 83rd. Okay, so again, I'm going to go back to my table instead of trying to read that really cruddy graph. And the closest I get to it is an 83, and an 83 would have happened right at the 60. So I'm going to estimate it as close to there as I can. I'm going to say approximately $60,000. Okay, all right. So that was it for cumulative relative frequency graphs. They're just the regular percentage graphs that add up to 100. Next thing we're going to talk about is a standardized score. So for a standardized score, I'm going to skip around down here a little bit. Okay, the first thing I'm going to do is I'm going to go down to this formula. This is a super important formula. This is one that you should always know how to do. And it is taking your x minus the mean value over the standard deviation. And that is called a z-score. Okay, so what that basically means is we are telling you how far off average you are. So if your z-score was 0, a z equals 0 means that you were exactly the same as the mean. So when you subtract them, you get a 0. 0 over anything is 0. So a z-score of 0 means you are perfectly average. If you are above average, your z-score should be positive. And if you have a negative z-score, you are below average. Okay, and then the numbers are standardized in that instead of looking at what the specific numbers are to the problem, we can just say you are this many blocks above average, this many blocks below average, and we call those the number of standard deviations, okay? All right, so I'm going to go back up to the top here and fill in some of these. So z-score is a standardized score. It's good. It's great for comparing two sets of data that were completely different numbers, different middles and stuff like that. And it's a way to standardize the score. So if we get a standardized score of a 1, it means that this score is 1 standard deviation above average, above the mean. Okay, this one means that the standard score is 2.5 below average, below the mean. Now notice I did not say it's negative 2.5 below. Okay, it's 2.5 away from the mean in the negative direction, so left, so below the mean. Okay, next one. In 2012, the average number of wins in Major League Baseball was 81, with a standard deviation of 11.9 wins. Okay, so it says calculate the z-scores for each one of these. Now we're going to use that formula. So we have an 81 versus the average 81 over 11.9. This is going to be a z-score of 0. That means that they were exactly average, the team that would have scored 81 wins that year. The ones that scored 70 minus 81 over 11.9, let's see, that is going to be 11 over 11.9. So that's going to be somewhere right around 1, but it is going to be negative 11. So it's going to be below average, right? Because 70 is below the 81. And then that's going to be negative 0.9. So almost 1 standard deviation below the mean. And then 95 minus 81 over 11.9 is 14 over 11.9, which is about 1.2. And again, 95 is above average, so the z-score should reflect that. It's 1.2 standard deviations above the average. All right. Here's the great use for it is you can compare two different things. Okay, so I'm going to move down here. I'm going to skip this one so you can skip it too. Okay, because there's another one just like it down below. Eleanor has a 680 on a math part of the SAT. And then the SAT we know has a mean of 500 and standard deviation of 100. She also takes the ACT, and she gets a 27 there, and that has a mean of 18, standard deviation of 6. Question is, which one should she use? Which is the better score for her? Obviously, both scores are above average. So the question is, which one is more above average based on their standard deviation? Standard deviations are just standard blocks away from the mean. So in the first one, we're going to write it as Z for her SAT score, and her score was 680. The regular average was 500. Standard deviation was 100. So that is going to give us 180 over 100, which is 1.8. So that is 1.8 standard deviations above the mean. Okay, her ACT score, so I'm doing Z with a sub ACT. Her ACT score is, ACT is 27 minus 18, and that's standard deviation of a 6. So now I've got a 9 over 6. That's a 1.5. So what score should she use? She should use her SAT score was higher. It was almost 2 standard deviations above the mean, whereas her ACT was just 1.5 standard deviations above the mean. So she did better. So we would say Eleanor did better on her SAT scores because her Z-score for SAT was greater than her Z-score for ACT. Okay, and then they ask, okay, if Eleanor's score of 680 on the SAT math section places her in the 82nd percentile, what does this mean? So we're just interpreting what 82nd percentile means. 82nd percentile means that approximately 82% of the SAT scores were below her score of 680, right? So it's the percent of people or percent of things that are below the place where you're standing. Okay? All right, so that's pretty easy, right? So that's a Z-score. We're going to use those lots. Okay, second one we're going to talk about is a normal distribution. So normal distributions are symmetric, single-peaked, bell-shaped. These you probably have heard is called just bell-shaped curves or bell curves. So there's lots of different shapes to them. I mean, they still have the same shape, but like here's one that is very tall and narrow. And here is one that is very flat and doesn't go up as much. They are both considered bell curves. So when they say sketch, we don't really care which one you sketch, just that you try to have some kind of ovally shape in the middle and that the tail and the bottom kind of goes down towards the x-axis. It shouldn't go back up again. Okay, so both of those are normal curves. Okay, all right. If we know it's an approximately normal curve, so this doesn't work for every z-score or anything else, just if they tell us that it's a normal curve, this is an approximation that we need to know, and you are to memorize all these percentages, okay? So here is what those look like. Hang on a second. I'm back. All right, so here's what those look like. So this says sketch a normal curve with a mean of 20 and a standard deviation of 3. Okay, so if I do that, I'm going to draw just a general one. Again, here's my baseline, here's my curve. Okay, this hill is where you put the center. That's our average. Most people score average. That's a 20. And then we're going to block them off so that we can see at least 3 sections evenly spaced on each side. So I'm going to do like one here, and one here. And then the same thing on the other side. I'm just trying to evenly space these. One here and one here. And then I'm going to move them each by 3. So adding from 20, this is going to be 23, 26, 29. And then subtracting 3, this is going to be a 17, a 14, and 11. So if the average score is a 20, then most people will get a 20. A few people will get between 17 and 23. Some people will get between 14 and 26. Very few people will go lower than 11 or higher than 29. Okay, so here's where these percentages come in. Okay, first one, 68% are within 1 standard deviation of the mean. That means in this section right here, if their score is between 17 and 23, they are part of the middle 68%. And if they're part of the middle 68%, we know 34 are slightly below average and the other 34 are slightly above average. Okay, so we know what each one of those sections are. So if I asked you what percent in this problem of the people were scored between 20 and 23, you could say, oh, it's 34%. It's half of the way between the 2 first standard deviations, right? All right, so the next one would be between the next 2 standard deviations. So this is between 2 standard deviations to the left, 2 standard deviations to the right. This total amount would be, so from here to here, would be 95%. Okay, so 95%. So if this is still 34 and this is still 34, how much is these 2 parts over here? So I'm going to do 95 minus 68 that we've already used up. That's a 7 and a 27. Divide that by 2, and that is 13.5% end up in this section and 13.5% end up in this section. So if I were to ask you what percentage fall between 14 and 17, 13.5% of those people or of those things, okay? All right, next one. So that was the 95. So now we've got 99.7. So 99.7 is going to go from the third standard deviations over, and that is 99.7% to go that way. Okay, and then if that's 13.5, how much are in those little leftover ones? So let's see, for this one, I would do 99.7 minus, ooh, do I want to minus all that? Minus 95 from before. That'd be a 7, a 4.7, right? And divide that in half, and that will be 2.35 for these little sections right here, 2.35. Right? Now, there's still some extra ones down below there yet. We still have this little section in here, and we still have this little section down here. So how do I figure out what those two are? Well, I know if I go all the way across forever, so those go out forever, I would be looking at 100%. So 100% minus 99.7 is going to leave me 0.3. Split that in half. This is 0.15%. That is already a percent with a decimal in it. 0.15%. Okay, so another way that you could label these, and again, if they say to label the mean curve starting with 20 and 3, those are the numbers that you're supposed to use, but also consider that if we're talking about z-scores, the middle of every normal curve will be a 0 no matter what. If you move over 1, it will be a 1 no matter what, and then a 2, and then a 3. And this would be a -1, a -2, and a -3. So it standardizes everybody's normal curve where the top number, the most frequent, the mean in the middle is always a z-score of 0, and then you have the z-scores on the outer sides. So now we're going to do some with adding up those percentages. Okay, now keep in mind, you could look back at this chart and just look at all the percentages, or you can calculate them, figuring out which way is the easiest. Remember too that it is 50% on the left of the 0, 50% on the right of the 0, 100% for the whole thing. All right, so let's go through and do a couple problems with this graph. Nope, we're going to do another one. We're going to do another normal curve that is a mean of 66 and a standard deviation of 3. So we're going to sketch this curve first. Close enough. So this is going to be the 66. I'm going to try to do 3 sections going this way, and then add 3s for each one, and then do 3 about equally spaced going this way. Move 3s for them. All right, so we've got those. All right, and then I'm going to put my z-scores too, just to make sure that I have them and I know where my standard deviations are. 2, -3. All right, so it says approximately 95% of the heights will be between which two values? So I know 95% of the heights are going to be between plus and minus 1 standard deviation. So 1 standard deviation is going to be 63 to 69 inches tall, would be 95% of the population that they're talking about, okay, at heart high. What proportion of students would be shorter than 63? Well, if I'm going to do 63 for this one, then I'm trying to figure out what is all of this section in here. So all of this section in here. So how do I figure out how much that is? Well, let's see, if I want to go less than 63, I could just add up their little pieces, or look at how close that is to 50. I think I'm going to do 50% for the whole left side minus the 34 that I know is that middle one. That's going to give me 16%. Okay. All right, next one. I'll start doing the calculations next to the graph so you can see them there as we're counting. Taller than 72. So taller than 72 is this section right in here. So taller than 72, I'm just going to use those two that I know. So I'm going to call that 2.35 plus 0.15 is going to be 2.5%. Okay, and then let's see, what else do we have? 63 and 72, 63 and 72. So if I do 63 and 72, I'm doing all of this part. So I already know this is 68, so if I know this much, then I can add to that. Okay, so that's what I'm going to do. So I'm going to do 68 plus 13.5 was that other part. So this is 81.5%. And then between 57 and 69, 57 is this way, all the way to here. Okay, so how am I going to do that one? I think I'm going to start out with the 68% in the middle and then add up those extra two pieces. So that's going to be 68 for the two middle pieces, and then 13.5 for the next section to the left, and then 2.35 for that section right before the very last amount. Okay, so this is going to be a 5 and an 8 and an 83%, 0.85. Okay, so fairly easy stuff. That is it. That's all we're doing for today. Hopefully that was okay. All right, we'll see you next time.